Okay, for Pure Paper 2 from the March 2022 mocks. Question number 1. f of x is 3x cubed plus 2ax squared minus 4x plus 5a. Given that x plus 3 is a factor of f of x, find the constant value a. Okay, so x plus 3 is a factor. By the factor theorem, f of minus 3 will equal 0. Okay, so whatever value of x makes that 0 means that this must equal 0. So we're going to have 3 times minus 3 cubed plus 2a times minus 3 squared minus 4 times minus 3 plus 5a, and we want that to equal 0. That's a linear equation in A. We've got 18a plus 5a, that's 23a. And then we also have negative 81 plus 12. That's going to come across to the other side. So that's going to be positive 81 minus 12. On the calculator then, let's clear all that. All right, 81 minus 12 over 23, and we get A is 3. And that's the answer. Question number 2. Okay, figure 1 shows a plot of the curve with equation y equals cos of x, where x is measured in radians. Diagram 1 on the opposite page is a copy of figure 1. Use diagram 1 to show why the equation cos x minus 2x minus a half equals 0 has only one real root, given a reason for your answer. Okay, so I've got cos of x here. So if I consider cos of x equals 2x plus a half, by taking this equation and adding 2x plus a half to both sides, then if I look to plot that, then it should only intersect the curve once. So, onto my figure. Okay, this is the copy of figure 1, so this is diagram 1, and it's going to have a gradient of 2. Let's just check the values there. So cos of x does go up to 1, so that is 1 on the y-axis, that is minus 1. And it's measured in radians, so that should be pi. So we are looking at 1, 2, 3, 4, 5, 6. Okay, so it looks like these are in ones as well. No, these are in halves, so that's 1. That's 1 there. That's 2 there. That's 3 there. Oh no, that's 2 pi. Oh, that's 1. Yeah, 2. So it is in ones on the x-axis as well. So that's fine. So we want 2x plus 1. So sorry, 2x plus a half. So we want a gradient of 2 going through a half. So it's going to go through that point, that point, that point. Okay, and then you can use a ruler, or you can sketch it on. That's fine, that'll do. So we have y equals 2x plus a half, and it only intersects at one point. Okay, so cos of x and 2x plus a half intersect at one point. And therefore, there's only one solution. There's only one root. Let's call it alpha is positive. Okay. Part B. Given that the root of the equation is alpha and that alpha is small, use the small angle approximation for cos of x to estimate the value of alpha to 3 decimal places. Okay, so part B. Cos of alpha is approximately equal to 1 minus a half alpha squared. Okay, that's a small angle approximation for cosine. That's just something you need to know. And we want this to be equal to 2 alpha plus a half. This is now a quadratic equation in alpha. I'm going to times it by 2 to get rid of my fractions. And then I'm going to simplify it. So I'm going to bring that across to this side. So I'm going to get an alpha squared plus 4 alpha. And I'll have plus 1 minus 2. So it's minus 1. Okay, so that gives me that quadratic. Solve the quadratic, so alpha is minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. So that's minus 2 plus or minus root 20 on 2, but root 20 is 2 root 5, so that's plus or minus root 5. Okay, so we want alpha to be positive. We can see it's positive from the sketch. Okay, the root intersects where x is positive. So therefore we want positive root. So therefore alpha is going to be minus 2 plus the square root of 5, or actually approximately 2, because we've used a small angle approximation. And it says it wants it to 3 decimal places. So we're going to do minus 2 plus the square root of 5. And that is 0.236. Okay. Question number 3. We're given this definition of y, or x does not equal minus 1. Show that dy by dx is this thing where a and n are constants to be found. Okay, so dy by dx, so we're going to differentiate this. This is a quotient, so we're going to use the quotient rule. So part A, u is going to be 5x squared plus 10x, which means u primed is 10x plus 10. V primed, v is the denominator, which is x plus 1 squared. And v primed is the differential of that, which is 2x plus 1. Okay, plug that into the formula, which is vu primed minus uv primed over v squared. It is given in the formula book. So v times u primed, so that's going to be x plus 1 squared times 10 into x plus 1. So I've taken x plus 1 out as a factor there. And minus vu prime, so it's that times that. So we're going to get, again, I'm going to factorise out something here, so it's going to be 5 into x squared plus, I could take out 5x into x plus 2. So it's going to be 10x times x plus 1 times x plus 2. Okay, shouldn't really write on that area in the actual exam, but it's okay for this illustration. Divided by v squared, so then we're going to square that. So it's going to be x plus 1 squared, which is x plus 1 to the 4. Okay, we need to show that it's this thing, so we're going to need to do some cancelling of things, and hopefully the top will come down to be a constant. Should be good. Okay, so I'm noticing there's an x plus 1 on the bottom, and everything on top has an x plus 1, so there's an x plus 1 term here, and there's an x plus 1 term here. There's actually 3 x plus 1s there, but we're going to cancel one of them because of that one. So I'm going to say that is 10 into x plus 1 squared minus 10x into x plus 2, and that is divided by x plus 1 cubed. So expand those brackets, let's see what cancels. So we're going to get 10x squared plus 20x plus 10 minus 10x squared minus 20x. This is looking promising. All divided by x plus 1 cubed. And we can see the 10x squared will cancel and the 20x will cancel, leaving us with a 10. So it's 10 over x plus 1 cubed. There we go, that is of the right form. Okay, a over x plus 1 to the n. A is 10 and n is 3. It doesn't say to state a and n, it just says to write it in this form, so we don't have to state it, but we can if you want. And therefore a is 10 and n is 3. Part B, hence deduce the range of possible values of x for which dy by dx is negative. So for this to be negative, x plus 1 must be negative. So y primed to be negative implies x plus 1 needs to be negative, because the 10 is obviously always positive. And that means that x is going to be less than minus 1. That's it. Okay, question 4. Find the first 3 terms in ascending powers of x of the binomial expansion of 1 over 4 minus x rooted, giving each coefficient in its simplest form. Okay, so this is a second year binomial expansion because n is not an integer. So we can check the formula book for this. So we want A-level maths. Here we go. Binomial series. That's where n is an integer, so that's no good. But this one is where n is any real number. So this is the one that we want. Okay, now how far do we need to go? First 3 terms. So that means we're going to have the constant term, the linear term, and the quadratic term. Okay, so we're going to use those 3 terms there in our formula. So first things first, we need to write this thing as a single power. So we're going to get 4 minus x to the power of negative 1/2. Okay. Negative because it's 1 over, and 1/2 because it's the square root. The problem is the binomial exponential formula has to have a 1 here, so we're going to pull out the 4 first of all, so it's going to be 4 to the negative 1/2 into 1 minus x over 4 to the negative 1/2. Okay. That is just 1/2. Okay, you can evaluate that. And then this is what we're going to use the binomial expansion formula on. So it says it is 1 plus nx. Now n is minus 1/2, and x in this case is minus x on 4, so it's going to be a negative times a negative, which is going to be positive. So just be careful with your signs. And that's going to be x over 8. And then the next term is n times n minus 1 times x squared. So again, just be careful here. N is negative 1/2 times n minus 1, which is going to be negative 1.5, times x squared, which is obviously x over 4. But we will just put 1 over 4 squared. Okay, and then we need to divide that by 2, because it's over 2 factorial. And that gives us 3 over 128. Okay, so that's going to be plus 3 over 128x squared, and they're all positives. That's the first 3 terms. It would carry on indefinitely, but it only wants the first 3 terms. Okay, just checking the answer so far. Yep, and then we can bring the half back in. So that is going to be 1/2 plus x on 16 plus 3 over 256x squared, and that is the answer, 4 marks. Okay. The expansion can be used to find an approximation to root 2. Possible values of x that could be substituted into the expansion are x is minus 14 because this is true, x is 2 because this is true, and x is minus 1/2 because this is true. Without evaluating your expansion, state, giving a reason, which of these 3 values should not be used. Well, when you're dealing with a question like this, it should be the biggest value that's not used, and that would generally be because it's out of range. So this expansion is only valid. For the modulus of x over 4 is greater than 1, or if you like, minus 4 is less than x is less than 4. So therefore, we cannot use x equals minus 14 because the expansion is not valid. And no matter how many terms you include in the expansion, it will not converge to this when x is minus 14, okay, because that's out of range. Okay, so that's the one we shouldn't use. Part 2, state, giving a reason, which of the 3 x values would lead to the most accurate approximation of root 2, and the answer is minus 1/2. And this is because minus 1/2 has the smallest magnitude. Okay, so what happens is this expansion is exactly true for when x is 0. Okay, if x is 0, then this is 4 to the minus 1/2, which is 1/2. And when x is 0, all the terms past the linear term disappear, and we get 1/2. So this is exactly true when x is 1/2. No, sorry, when x is 0. The further you get away from 0, the less accurate it is. So because 2 is 4 times further away from 0 than 1/2, then this is going to be more accurate. Okay, so we should use x is minus 1/2. Okay. 5. F of x is this quadratic. Write f of x in the form a into x plus b squared plus c, where a, b, and c are integers to be found. So this is completing the square. A couple of different ways you can do this. You can either expand this and equate coefficients, or you can complete the square directly on this, which is what I'm going to do. So the way I complete the square is I pull out the coefficient of x squared. All right, that's obviously the same thing. And then I complete the square on what's inside the square bracket. So it's going to be x plus 1 squared. That'll give me the x squared, the 2x. It also gives me a plus 1, which I don't want, so I need to minus 1 plus 9. Okay, these two lines are identical. And now I bring the 2 back in. There are slightly different ways you can do this, but this is just the way I prefer. I'm going to get 9 minus 2, which is minus 7. And that's the answer. Part B. Sketch the curve with equation y equals f of x, showing any points of intersection with the coordinate axes and the coordinates of any turning point. Okay, so the turning point is going to occur when x is minus 1, because that's going to be when this is 0, and the y value at that point will be minus 7. So it's a positive quadratic, so let's pop that on first. There we go, positive parabola. This point here is minus 1, 7. Oh, sorry, minus 1, minus 7. So we should... Oh, no, sorry, that's a plus 7. Here we go, plus 7. 9 minus 2. So that's positive, it is positive 7. So therefore the y-axis should go to the right of that point, like so. And the x-axis should go underneath that quadratic, like so. And the only point it crosses an axis is here, and that's going to be when x is 0. And we can see that when x is 0, f will be 9. So it's going to cross at 9. There we go. Y equals f of x. Part C. Fully describe the transformation that maps the curve with equation y equals f of x onto the curve with equation y equals g of x, where this is true. Okay, so the thing to do here is just to try and look at what's going on between here and here. And the most obvious thing that stands out is that, first of all, x has been replaced with x minus 2. But that's not true for this x. So I'm going to force that out. I'm going to force out that this x is also going to be replaced with x minus 2. So the way I'm going to do that is I'm going to say g of x is equal to 2x minus 2 squared. I'm just going to copy it down first of all so you can see it. X minus 2 squared. Then I want plus 4 into x minus 2. That's going to give me minus 8. But I don't want minus 8, I want minus 3, so I need to add 5 to correct that. So these two lines are now identical. And then I'm also going to say that this is 2 into x minus 2 squared plus 4 into x minus 2 plus 9 minus 4. And the reason I've done that is because f is 2 times something squared plus 4 times something plus 9. Okay, so that is f in there, just of minus 2. So this is actually f of x minus 2 minus 4. And now, when it's written like that, it's obvious to see what's happened. Therefore, it's a translation by the vector 2 minus 4. So it's going to move 2 in the x direction. So that point there is going to now be at positive 1, and then it's going to move 4 down. So it was at 7, it's now going to be at 3. Okay, not that we need to sketch that, but that's what would happen. And then finally, part C, part II, find the range of the function of this. Now this is 21 divided by f. Okay, there's f, 2x squared plus 4x plus 9, denominator 2x squared plus 4x plus 9. So this is 21 divided by f. So because this is always positive, okay, we can see this is always positive, it's always above the x-axis, and that means h is always going to be positive. And also the minimum value of this is going to be the maximum value of h, because when you divide by the smallest number you get the biggest number you can. So h of x is going to lie somewhere between 0 and whatever 21 divided by the minimum is. Now the minimum was at 7, so 21 divided by 7 is 3. So h of x will always be less than 3. That's the answer there. In fact, it does equal 3 as well, because this does equal 7 when x is minus 1, so it can equal 3. Can't equal 0 because the parabola would need to be infinite at that point for that to be true, and it gets arbitrarily close to 0 because these get as big as you want. Okay. Question 6. Solve this trigonometric equation for theta values between minus 180 and 180. Okay, so this is a year 13 trig one because we've got a double angle in there. So as soon as you look at that, you should think, okay, let's get rid of that double angle. So for part A, I'm going to replace 5 sine 2 theta with 10 sine theta cos theta, because sine of 2 theta is 2 sine theta cos theta. Sorry, sine 2 theta is 2 sine theta cos theta. And that's going to equal 9 tan of theta, but that is actually just 9 sine of theta divided by the cosine of theta. So this is what we get. Okay, sine of theta equals 0 is a solution. Okay, don't just divide by sine theta. You will negate 3 solutions here. So just be really careful. This implies that there are 3 theta values from that, which is minus 180, 0, and 180 degrees. Now we can divide by sine theta. Never divide by a variable unless you consider when that variable is 0. Okay, very important and very easy to lose marks. So we can divide by sine theta. We can times by cos theta. That can go up there. So we're going to get cos of theta is 9/10. Okay, and there will be 2 solutions to that. Oh no, cos squared of theta is 9/10. There'll be 4 solutions to that. So either cos theta is the positive or the negative of 3 root 10 over 10. Don't forget the negative root as well. Okay, easy to miss that. So let's draw the cos curve between these ranges. It's going to start down here and up there. There we go. So between minus 180 and 180. That gives us 2 solutions here. So there'll be 1 there and 1 there from the negative. And then the positive up here, there'll be 1 there and 1 there. Okay, so we're looking for 4 solutions. And it says to 1 decimal place where necessary. Okay, so we should give these to 1 decimal place. Okay, so calculator. In radian mode at the moment, so we need to change into degrees, make sure we're in the right mode. Okay, inverse the cosine of 3 root 10 over 10 gives us 18.43. And that'll be a negative as well because cosine is symmetrical. So plus or minus 18.4 degrees. And then the other one will be when it's negative. So I'll go back into that one. I can just pop a negative in there and I get 161. That's this one. And of course you've got the negative of that as well. So plus or minus 161.6. And I've left them to 1 decimal place because it says that. Okay, if you leave it to more than that in this case, you would actually lose marks. Okay. All right, so those are the 7 solutions. 1, 2, 3, 4, 5, 6, 7 to this equation. Part B, deduce the smallest positive solution to this equation. Well, the thing to notice here is that to get from here to here, we've replaced theta with x minus 25. Okay, replacing theta with x minus 25 in both situations. So theta equals x minus 25. This implies that x equals theta plus 25. So we just need to choose the smallest value of theta that will make that positive. So I could choose 0. That would give me an x value of 25. That's quite small. However, actually, if I choose theta as minus 18.4, when I add 25 to it, it will become positive. So the smallest x, or smallest positive x, will equal minus 18.4 plus 25, which is 6.6 degrees. There we go. Question 7. In a simple model, the value v of a car depends on its age in t years. The following information is available for car A. Its value when new is £20,000 and its value after 1 year is £16,000. Use an exponential model to form, for car A, a possible equation linking v with t. Okay, so we're told it's an exponential model that we need to work with. So that means the value of the car is going to be something times something, let's call it small a, to the power t. Okay, that's an exponential model. An exponential just means that the exponent is the variable. And we know that when t is 0, v is 20,000. So that means capital A is 20,000. And we also know that when t is 1, v is 16,000. So we're going to get 16,000 equals 20,000 times a to the power 1. So that gives me that a is 16 over 20, or 8 over 10, or 4/5. So therefore the model is v is equal to 20,000 times 4/5 to the power t. Okay, that's an exponential model that fits. T is 0, v is 20,000, t is 1, v is 16,000. There are a couple other ones you can have. You can have a different base. The most common base that's not 4/5 is e. So you might have e to the something times t. And if you do that, then k comes out to be the natural log of 4/5. Okay, so you could do that, and that's fine. You'll get the natural log of 0.8 times t. Okay, and that's an also fine model. This is slightly better because you don't have an e to the power of a log, which will cancel itself. Okay, the value of car A is monitored over a 10-year period. Its value after 10 years is £2,000. Evaluate the reliability of your model in light of this information. Okay, so part B, we're going to plug in t as 10. This implies that v is a model, so it's approximately, it's going to be 20,000 times 0.8 to the power of 10. We get 2,147, or 2,150 to three significant figures. So 2,150. That's almost 2,000. So I would say the model is pretty good. The model seems to be good. Okay, and the following information is available for car B. It's got the same value when new as car A, and its value depreciates more slowly than that of car A. Explain how you would adapt the equation found in A so that it could be used to model the value of car B. It's going to depreciate more slowly, which means it takes longer to go down, which means the value of A will be bigger. So the value of A will increase, but not exceed 1. Not equal or exceed 1. Because it still depreciates over time. The car doesn't get more valuable over time in this model, so it's not going to get bigger than 1. Okay. So it's going to be somewhere between 0.8 and 1. If you did this thing, k comes out to be like minus 0.22 something, I think. So you want to make it less negative, that value. So minus 0.1 as an example. Okay. Right, question 8. Figure 2 shows a sketch of part of the curve with equation y equals x times x plus 2 times x minus 4. The region R1 shown in figure 2 is bounded by the curve and the negative x-axis. Show that R1 is 20/3. Okay, this is just a simple integral. We can see from this that it's going to cross the x-axis over here at positive 4. It's going to cross the x-axis here. Oh, not positive 4. Negative 2, going to cross the x-axis here at 0 and cross the x-axis here at positive 4. Okay, we can get that from the roots of the equation here. So we need to integrate this function between negative 2 and 0. It's not enough just to do it on the calculator. You have to actually complete this integral. So we're going to integrate between minus 2 and 0. This cubic is x times x plus 2 times x minus 4 dx. And that's going to equal the integral from minus 2 to 0 of x cubed. then we're going to get a 2x squared minus a 4x squared, so that's minus 2x squared. Then we're also going to get minus 8x dx. Okay, so you have to expand the bracket to come to that integral to then compute it. You have to see this integral being integrated, so you need a quarter x to the 4 minus 2/3 x cubed minus 4x squared between minus 2 and 0. Then you just plug that in, so you're going to get a 0 when you plug in x is 0. Then you're going to get a minus a quarter times minus 2 to the power 4 minus minus 2/3 to minus 2 cubed minus 4 times minus 2 squared. That's a lot of negative. That's all negative, isn't it? Okay, what have I done wrong? Minus minus. Yes, minus minus. That's plus. There we go. Okay. And run that through the calculator. We're going to get minus a quarter times minus 2 to the power 4, which is positive 16, plus 2/3 times minus 2 cubed, which is minus 8. And then we're going to get plus 4 times 4. That gives us 20/3. Which is what the question said it was. Okay, 20/3. And the fact that I've put in x is 0 and x is minus 2 and stated that, that's enough then for the examiner to know that I have actually done the calculation all correctly and I know how 20/3 comes about. So that's fine. Okay, the region R2, also shown shaded in figure 2, is bounded by the curve, the positive x-axis, and the line with the equation x equals b, where b is a positive constant somewhere between 0 and 4. Given that the area of R1 is equal to the area of R2, verify that b satisfies this equation. Okay, so we want the integral from 0 to b of this cubic, which is x cubed minus 2x squared minus 8x dx, to be equal to negative 20/3. And I want it to be negative 20/3 because the area is below the x-axis. So therefore the integral will be negative the area. Okay, that's important. Now we just complete the integral, plug in b as the upper limit and rearrange, and hopefully that cubic, that quartic in b will pop out. So let's try it. So we're going to get a quarter x to the 4 minus 2/3 x cubed minus 4x squared. Okay, that's the same expression as we had in part A, between 0 and b. So we're going to get a quarter b to the power 4 minus 2/3 b cubed minus 4b squared, and we want that to equal minus 20/3. Okay, so it's a quartic in b. I'm going to times it all by 12 to get rid of the fractions, and I'm going to bring this across to the other side. So that's going to be 3b to the 4 times that by 12. So that's going to be minus 8b cubed minus 48b squared. And then I'm going to add to that, so let's add 80 equals 0. So that's my quartic in b. I could try and factorise that, or I could perhaps look at what the answer is given and work from that. Personally, I prefer working this way forwards. So I know that b plus 2 will be a factor, because that's actually given in the question. So 3b to the 4 minus 8b cubed minus 48b squared plus 0b plus 80. and I could do long division. So 3b cubed, 3b to the 4 plus 6b cubed, subtract minus 14b cubed minus 48b squared. So that's going to be minus 14b squared. So that's minus 14b cubed minus 28b squared. That's going to be minus 20b squared plus no b. So it's going to be minus 20b. So minus 20b squared minus 40b. That's going to give me a 40b. So plus 40 plus 80. 40b plus 80. 0. Okay, so that factorizes into that cubic, and then I could factorize it out again. So I know that b plus 2 also goes into that cubic, and I know that because b plus 2 is a double root, and when I complete this, I should end up with this quadratic on top. So that's going to be 3b cubed minus 14b squared minus 20b plus 40. So that's going to be 3b squared. That gives me 3b cubed plus 6b squared. That's minus 20b squared. So that's minus 20b. Minus 20b squared minus 40b. That's going to be a 20b plus 40 plus 20, 20b plus 40, 0. And we can see that this quadratic does indeed match this quadratic over here. So therefore, the integral gives b plus 2 squared into 3b squared minus 20b plus 20 as required. Okay. You don't have to do long divisions, but I think it's clear what you're doing. Just be careful for show that questions where the answers are in the question. Okay, the roots of the equation 30b squared minus 20b plus 20 equals 0 are 1.225 and 5.442 to 3 decimal places. The value of b is therefore 1.225, and that's because we know that b lies between 0 and 4. Explain with the aid of a diagram the significance of the root 5.442. Okay, so with this one, a couple of different ways that you could do this. Part C. Let's just draw the cubic, something like that. That's 4. That is 5.442. We could say that all of that area plus that area plus that area equals 0. Okay, or arguably this area plus the negative of this area still leaves the minus 20/3, which we wanted, which will then cancel with that. So there's a couple of different ways you could argue this. Personally, I would just draw all of that and say the area above the axis equals the area below the axis. Okay, that would be my answer. But yeah, you could argue that this number here, which is 1.225, that area there is equal to that area there. So when the integral happens, because this is a negative area, those two would sum to 0. So the integral from 0 to 5.442 would still be the minus 20/3, which you wanted, which was this area here. Okay, so you could argue it that way as well. Okay, 9. Given that a is greater than b is greater than 0, and that a and b satisfy this log equation, show that a is equal to b squared over b minus 1. Okay, so we are just going to use some log laws here. So when you've got subtraction of 2 logs, then you can replace it with a single log and a division inside. So the left-hand side is going to become the log of a over b, and the right-hand side is still the log of a minus b. Now I've got log of something equals log of something, therefore the two somethings must be equal. Mathematically, you're raising both sides as a power of the base of the log, which in this case would be 10. So it gives us this equation. And now we need to make A the subject of this, and this should fall out. So A is going to be equal to AB minus B squared. Bring all the A's across to one side, so we get A minus AB equals minus B squared. Factorise out the A, and then divide, and then times top and bottom by -1. And that's what the question says. Okay, B squared over B minus 1. Good, nice simple 3 marks. Part B, write down the full restriction on the value of B, explaining the reason for this restriction. Well, this currently says that B has to be positive, and the reason for that is because you can't log a negative number. Okay, so B is positive, and that's because you can't log a negative number. But we also need then that A is positive. So we require A to be greater than 0, and that's because you can't log a negative. Therefore, B squared over B minus 1 needs to be positive. This implies that 1 over B minus 1 must be positive because B squared is always non-negative, which means we require B to be greater than 1. There we go. We still also require B to be less than A because we don't want this to be negative either. So the full restriction then is A is greater than B, which is greater than 1. But I think you get them full mark if you just left that as your answer. Okay. Question 10. Prove that for all n natural numbers, n squared plus 2 is not divisible by 4. Okay, there's quite a few different ways you can tackle this. I will tackle it by considering that n is even and then n is odd as separate cases. So, first of all, n is even. This implies that n can be written as 2m. This implies that n squared plus 2 is 4m squared plus 2. So this is a multiple of 4 plus 2. Therefore, not a multiple of 4. Okay, algebraically we could try and divide that by 4. So 4m squared plus 2 over 4, that's m squared plus a half, which is not an integer. Because it's not an integer, then the original wasn't divisible by 4. This is never an integer when m is an integer. So it's not true when n is even. That's only half the story. We have to also consider n is odd. This implies that n is equal to 2m, either plus or minus 1, doesn't matter. I can do plus 1. This implies n squared plus 2, okay, a little bit trickier now because we've got to square this thing, is equal to 4m squared. Square that, you've got to do the cross multiples, so we're going to get plus 4m. You're going to get plus 1, and then don't forget the plus 2, so it's plus 3. Well, that's clearly odd, so it's definitely not divisible by 4. Therefore, n squared plus 2 is odd, therefore not divisible by 4. Okay, we can see it's odd because we've got an even, plus an odd. Alternative way to consider it is n squared. If n is odd, then n squared is odd. So when you add 2 to it, it remains odd. So clearly not divisible by 4. And an algebraic division, you could do 4m squared plus 4m plus 3. Attempt to divide that by 4. We'll get m squared plus m plus 3/4, which again is not an integer. So you can argue it that way. Either way, if n is even, it's not true. If n is odd, it's not true. Therefore, this isn't true for all n integers. Actually, n is only naturals. So Therefore, all n naturals. Simples. Okay, part 2. Given that x is real, the value of 3x minus 28 modded is greater than or equal to the value of x minus 9. State, giving a reason, if the above statement is always true, sometimes true, or never true. Okay, this is going to be a V shape because it's a translation or transformation, I should say, of the mod graph. And this is a linear graph, which means we've either got that situation, in which case the statement is always true, or we've got this situation, in which case it's sometimes true. So straight away, just by looking at the question, we know it's not never true. Okay, there has to be some value that it's true, because this mod will tend to positive infinity as x tends to infinity, negative infinity, whereas this will tend to negative infinity. So there's always going to be some point to the left where it's always going to be greater than. So we know it's either sometimes true or always true. Okay, either sometimes true or always true. Now the key point to check is this one, because if it's sometimes true, then that will be the point where it's not true. If that point is true, then that means it's always true. So this is the point we need to check. And that occurs when the content of the mod bracket is 0. So in this case, 3x minus 28 is 0. So I need to check that x value. Okay. So let x equal 28 thirds. This implies the modulus of 3x minus 28 is 0. But also x minus 9, well, I need to calculate that. So we're going to get 28 thirds minus 9, well, 9 is 27 thirds, so 28 thirds minus 20 thirds, that is then a third. Aha, it's not true when x is 28 thirds. So therefore it's this case. Okay, because the linear line was bigger than the mod graph at the vertex. So it must be this case, so therefore it's sometimes true. However, you can't just state sometimes true at the moment. You need to show a case when it is true. So pretty much most x values would be true, so I'm just going to choose x as 0. Let x equal 0. This implies the modulus of 3x minus 28 is 28. Don't forget the mods negate the negatives. And x minus 9 is equal to minus 9. Therefore, it is true when x equals 0. So we found a case when it isn't true. We found a case when it is true. Therefore, we can conclude it's sometimes true. Okay, but you do have to state a case when it is true. Okay, you can't just do the not true, or justify by a graph. You could argue it from this point of view, but you need to use words to describe it. You can't just have the picture. Question 11. A competitor is running a 20-kilometre race. She runs each of the first 4 kilometres at a steady pace of 6 minutes per kilometre. After the first 4 kilometres, she begins to slow down. In order to estimate her finishing time, the time that she'll take to complete each subsequent kilometre is modelled to be 5% greater than the time she took to complete the previous kilometre. Using this model, show that her time to run the first 6 kilometres is estimated to be 36 minutes and 55 seconds. Okay, well, the first 4 kilometres is a steady pace of 6 minutes per kilometre. So, the first 4 kilometres are just 6 plus 6 plus 6 plus 6. Okay. The time that she will take to complete each subsequent kilometre, so that's all the kilometres after the first 4, is modelled to be 5% greater than the time she took to complete the previous kilometre. So, the 5th kilometre is going to be 5% greater than the 4th kilometre, and the 6th kilometre is going to be 5% greater than the 5th kilometre. So this is how long it's going to take according to the model, for her to run the first 6 kilometres. So this is 6 times 4 plus 1.05 plus 1.05 squared. 6 times 4 plus 1.05 plus 1.05 squared. That comes to 36.915, which is obviously 36 minutes. So subtract 36, which equals 36 minutes. And then we've got a 0.915 minutes, so times that by 60, 54.9 seconds. Therefore, 36 mins and 55 seconds as required. Okay, 36 minutes, 55 seconds. Okay, great. Show that her estimated time in minutes to run the nth kilometre for r is between 5 and 20 is modelled as this thing. So just be a little bit careful with your explanations here. B, the 5th kilometre, that is going to be 1.05 times the 4th kilometre, which was 6. The 6th kilometre, that is going to be the 5th kilometre, 1.05 times 6, times 1.05, which equals 1.05 squared times 6. And the 7th kilometre is it going to be equal to 1.05 cubed times 6, and so on. And we need to notice that the power of the 1.05 is 4 less than the power than the value of the kilometre. So here the power is 1, and that was the 5th kilometre. Here the power is 2, that's the 6th kilometre. Here the power is 3, that's the 7th kilometre. So this exponential exponent is 4 less than which kilometre it is. So therefore the nth kilometre is going to be 1.05 times r minus 4 times 6, which is exactly what it says here. But writing out kind of this, so you're showing the examiner that you're spotting the pattern is sufficient for the mark. Okay, but it is a little bit harder to describe, particularly if you're good with exponentials, because this is actually quite obvious. But they've done it so that even if you can't do that, you can still do part C. On that note, part C, estimate the total time in minutes and seconds that she will take to complete the race. Should really say according to the model. Okay, so we want to add the first 4 6s for the first 4 kilometres, and then we need to sum this from r is 5 to 20 to give us kilometres 5 to 20, and then that will give us all 20 kilometres. Okay, so the first 4 kilometres is just 24, so that's nice and easy, plus this sum, so that's r equals 5 to 20 of 6 times 1.05 times r minus 4. Okay, so that's the sum I'm doing, but this is actually a geometric series. Now you could type in all 16 terms and gain full credit. I wouldn't recommend it. It's geometric. N is 16, there's 16 terms. Okay, don't forget to include the 5. Okay, it's not 20 minus 5, it's 5, 6, 7, 8, 9, 10, all the way up to 20. So there's 16 numbers there. So N is 16. A is the first term, so that's going to happen when R is 5. So we're going to get 6 times 1.05 to the 1, which is 6.3. And then the common ratio is this thing. Each time you increase the kilometre, you go up by 5%. So it's 1.05. So we can use the geometric formula from the formula book. S16 is equal to A times 1 minus R to the N divided by 1 minus R. Okay, so that'll be the sum of those 16 kilometres. So we can plug that in. 6.3 times 1 minus 1.05 to the 16 divided by 1 minus 1.05 gives us 149.04219181, blah, blah, blah. Okay, so that's the sum of the last 16 kilometres. Don't forget the first 4 kilometres. So therefore the total time is adding 24 to that, which is 173.0421, blah, blah, blah. So we need to convert that into minutes and seconds. So that's 173 complete minutes. And then if I subtract 173, that will leave me with a portion of a minute. Times it by 60 to give how many seconds that is. It is 2.5 seconds. 2.53. So therefore 173 minutes and 3 seconds would be the answer. Question 12. All right, f of x is 10e to the minus 0.25x times sine of x, and we're told that x is non-negative. Part A, show that the x coordinates of the turning points of the curve with the equation y equals f of x satisfy the equation tan x equals 4. So whenever it's mentioned turning points, you should immediately make the link to differentiation. So we need to differentiate this and set it to 0 for a turning point. So let's differentiate it. It's a product, so we're going to need the product rule. So part A, f primed of x, I can just take the 10 out as a factor. It's going to be, I'm going to say this times the differential of that. So that's going to be e to the minus 0.25x times the cosine of x, plus that times the differential of this, which is minus 0.25 e to the minus 0.25x times sine of x. Okay, so that's the derivative. Might take you a couple more steps to get to that. That's fine. We want to set that equal to 0. Well, we can divide by 10 because that's never 0. We can divide by e to the minus a quarter x because that's never 0. So this implies that cos of x minus sine of x over 4 equals 0. And now I'm going to add that to this side and then times by 4. So that's going to give me that 4 cos x equals sine x. Divide by the cosine. I get that 4 equals tan x, which is hopefully what it wants. Yes, tan x equals 4. Okay, there's your answer. Figure 3, which is this figure here, shows a sketch of part of the curve with equation y equals f of x. Sketch the graph of h against t, where h of t is the modulus of f of t, for t is non-negative, showing the long-term behaviour of this curve. Okay, so you need to think about what the mods do. So just check there's no blank space. There is a blank space. Put it in here then. So what the mod will do is it will take anything below the t-axis and it will reflect it up. So I didn't actually need to put my t-axis quite so high up. So anything that's below will just now become above because you're modding it. So anything that is negative, you just now becomes positive. So we're going to have the first bump, and rather than carrying through, it then just does the second bump. Just be careful because the time difference between when it hits the x-axis or t-axis isn't going to change. It's going to remain the same. So these points are the same distance apart, so just be careful with that. But the humps will get lower. There we go, that's the first 4. Make sure they're decreasing in height each time, just to make sure you get the mark there. Part C. The function h of t is used to model the height in meters of a ball above the ground t seconds after it's been kicked. Using the model, find the maximum height of the ball above the ground between the first and second bounce. Okay, so that's going to be, go to my graph, that's going to be here. And that's between the first and second bounce. There's the first bounce, there's the second bounce. That's the height there. So therefore, if we equate that back to this, that's going to occur here. That's the one I'm interested in. So it's the second time tan of x equals 4. Okay, the second time we have a stationary point. So tan of x equals 4. For t, tan of t equals 4. This implies then that t is going to be equal to the inverse tan of 4. But if I calculate that on the calculator, that'll give me this value of t. And to get to the next one, I need to add pi. Okay, because tan repeats every pi radians. Let's just check that model's good. Yep, that's fine. Okay, so it needs to be in radians now. Got to be in radians because I'm using calculus on trigonometry, so you have to be in radians. So inverse tan of 4, and then I'm going to add pi to that. So I get that t is 4.4674, blah, blah, blah. Okay, and now I need to plug that back into h. Okay, so h is here. You can ignore the mods, just then ignore the negative. Okay, so it's going to be 10 times e to the power of minus 0.25 times the answer that's stored in the calculator memory times the sine of that answer. And it's in radians already, so all good. And we get minus 3.17, so therefore we want the positive of that, which is 3.17. And what does it say? It doesn't say a particular value, particular significance. So play it safe, 3 sig fig is a good answer. Say 3.18 meters will do. Okay, part D. Explain why this model should not be used to predict the time of each bounce. And let's go back to my point earlier. These are equidistant on my t-axis. So this model would say that the time between bounces is equivalent, is equal between any two bounces, which is not true in reality. The time would decrease as the bounces got shorter. So it's not a good model because the times between bounces should not stay the same. There we go. Question 13. Okay, I think this is a Star Trek question. Yep. The curve C with equation, that thing, where P and Q are constants, passes through the point 3 half and has two vertical asymptotes with equation x equals 2 and x equals minus 3. Explain how you can deduce that Q is 4. Okay, so it's got a vertical asymptote at 2. So vertical asymptote at 2. That implies that 2x minus q when x is 2 it must equal 0. Okay, because a vertical asymptote on a graph occurs when the denominator of the fraction is 0, providing the numerator is also not 0. So this one we can see it's going to occur when x is negative 3, which is exactly when this asymptote occurs. So therefore this one must occur when x is positive 2. So we want 2x minus q to be 0 when x is 2. So if I plug that in here, this implies then that 4 minus q equals 0. Therefore q equals 4. Okay. Show that p is 15. Well, to get that, we're going to use this piece of knowledge. Okay, we know that when x is 3, y is a half. So that's going to give us a linear equation in p, which we can solve. So part 2, when x is 3, y is a half. So we're going to have a half is equal to p minus 9 divided by 6 minus 4 times 3 plus 3. Okay, so it's just plugging in x is 3. We know that q is 4 and y is a half. So this implies then that p, to show that question, just be careful. P minus 9 is going to be equal to a half times 2 times 6. Okay, so the half on this side times 2 times 6. which means P is going to equal 6 plus 9, which is 15. There we go. Okay. Again, just reiterate, just be careful to show that questions when the answer's in the question. Make sure that you are showing exactly how that answer is arrived at. Okay, don't fudge it because you won't necessarily get full marks for that. Figure 4, which is here, shows a sketch of part of the curve C. The region R, shown shaded in figure 4, is bounded by the curve C, the x-axis, and the line with equation x equals 3. Show that the exact value of the area of R is a log 2 plus b log 3, where a and b are rational constants to be found. Okay, so to answer this, well, we need to know the upper limit of the integral. And this occurs when y is 0, because it's the intersect with the x-axis. And when y is 0, the numerator is 0. So we get 15 minus 3x equals 0, so that tells us that x is 5. So we are looking to integrate between 3 and 5. Okay, so we're going to integrate this thing. So R, the area, is equal to the integral between 3 and 5 of this fraction. So that's 15 minus 3x divided by 2x minus 4 times x plus 3 dx. And we need to show that this thing is equal to a log 2 plus b log 3. Okay, so to answer this, we're going to use partial fractions. So I'm going to split this out into partial fractions. So that's going to be somehow identical to something over 2x minus 4 plus something else over x plus 3. Multiply this. Oh, it's not exactly identical. I'm going to put this over here, 15 minus 3x, 2x minus 4, x plus 3. Multiply by the denominator, so I get rid of the fractions. Okay, and then either plug in 2x values or equate the coefficients. Mathematically, it's a little bit better to equate the coefficients, so let's do that. Coefficients of x to the 1, I've got a plus 2b must equal minus 3, and x to the 0, I'm going to have 3a minus 4b must equal 15. Okay, so that's a pair of simultaneous equations. You could solve it properly, but I'm going to use the calculator just because I know they're fractions and just want to get it right, you know. So simultaneous equations, it's got two unknowns. It's going to have 1a, 2b's, and that's going to equal minus 3. And then it's got 3a's minus 4b's, and that's going to equal 15. And that tells me that a is 1.8 and b is minus 2.4. Okay, so plug those two back into here and then plug that back into the integral. Gives us that actually the region R is the integral from 3 to 5 of 1.8 over this thing, but I can just divide top and bottom by 2. So that's 0.9 over x minus 2 minus 2.4 over x plus 3 dx. Okay, now it's in that form, it's nice and easy to integrate because the top can be easily manipulated to be the differential of the bottom in both cases. So if I pull the 0.9 out of this integral, then the top will be the differential of the bottom, and similarly I can pull the minus 2.4 out from this side. So that's going to equal 0.9 times the natural log of the mod of x minus 2 at minus 2.4 times the natural log of the mod of x plus 3. Okay, definite integral, so square brackets between 3 and 5. Now plug in the values. So that's 0.9 times the natural log of 3 minus 2.4 times the natural log of 8 minus 0.9 times the natural log of 1 plus 2.4 times the natural log of 6. Okay, so that's what it equals, but we've got log 8 and log 6 kicking around, whereas the question was log 2 and log 3. So you need to reverse engineer some log laws to extract the 2's and the 3's. So I'm going to say this is 0.9 log 3 minus, now this is 2 cubed. So I could say that this is actually 7.2 log 2. Okay, this is 2 cubed, and I'll bring the 3 down the front. So 2.4 times 3 is 7.2. That's log 2. Log 1 is 0, so that just disappears. And then this, I'm going to say, is log 2 plus log 3. Again, reversing a log law. Okay, if you add 2 logs together, you times the contents. Okay, and now just collect the like terms. So I've got 0.9 log 3s here. I've got another 2.4 log 3s there. So that is 3.3 log 3. And then I've got minus 7.2 log 2 plus 2.4 log 2. That's minus 4.8 log 2. So that's my answer. And it is always worth just checking this just to make sure that you are right. So what I'm going to do here is I'm just going to pop the integral into the calculator. So math integral of 15 minus 3x. And don't forget that the FX 991s can do this as well. It's not just the graphical I've got here. 2x minus 4 times x plus 3 between 3 and 5. So that's the integral. That's the answer. And if I plug in this number down here, that should be the same decimal. So 3.3 log 3 minus 4.8 log 2. Ah, good. Okay, it's the same number. So I can now move on to the next question in full confidence that at working there is 8 marks for myself. If you didn't get it right, then perhaps just log that question in your head and come back to it later. Because you might still get better marks. On that note, there is only one question left, so you might realise you've got a bit of time to spend on the previous one. Okay, last question, question 14. The curve C in the standard Cartesian plane is defined by the equation x equals 4 sine 2y, where y is between minus pi on 4 and pi on 4. The curve passes through the origin. Find the value of dy by dx at the origin. Okay, so I'm going to differentiate implicitly. So part A, differential of x with respect to x is just 1. Differential of 4 sine 2y with respect to x is the same as the differential of 4 sine 2y with respect to y times dy dx. So that's going to become 8 times the cosine of 2y times dy by dx. Okay. That tells us then that dy by dx is equal to an 1/8 sec of 2y. Okay, so there's our derivative, but it wants the derivative at the origin, so I need to plug in y is 0, so dy by dx at the origin is equal to an 1/8 times 1, because sec of 0 is 1, which is obviously an 1/8. So the answer is an 1/8. Part B. Use the small angle approximation for sine of 2y to find an equation linking x and y for points close to the origin. Okay. So again, another small angle approximation. Sine of 2y is approximately 2y. Okay, it's a linear approximation. For sine, so we're going to end up with x is approximately 8y. That's my answer. And then explain the relationship between the answers A and B. The gradient of y equals an 1/8 x equals the gradient of the curve at the origin. And what you'll actually find is this line is actually tangent to this curve at the origin. And that's because if you replace sine x with x, then that is the tangent to sine at the origin. Part C, show that for all points x, y lying on C, this is true, where a and b are constants to be found. So this would usually be a further math integral, but it's kind of guided you through it a little bit, and you can use this definition of x in here to get the answer. So let's do that. All right, so part C, dy by dx, as we've already established, is an 1/8 sec of 2y, which I'm going to write as 1/8 cos of 2y. And I've got sine of 2y in terms of x. So let's try and get this as a sine. So using the relationship sine squared of something plus the cosine squared of something is always 1. That will tell us that the cosine of something will always equal, I'll put plus minus, 1 minus the sine squared of that thing. Okay, now because y is always between minus pi on 4 and pi on 4, then sine is actually always positive. So in this case, I can actually ignore the negative, and I can replace cos of x with positive, the square root of 1 minus sine squared of x. And that is because sine of 2y is greater than or equal to 0. No, it's not. It's because it's not at all. It's because cos of 2y is always greater than or equal to 0. Because that's the cos curve. Okay. So now if we take this definition then and plug that through, we'll end up with dy by dx is equal to 1/8 times cos 2y, but cos 2y is the square root of 1 minus sine squared of 2y. And I've done that because I've got sine of 2y in terms of x, which is x on 4. Okay, but sine of 2y is x on 4. So plug that in, I get dy by dx is equal to 1/8 times the square root of 1 minus x squared on 16. Actually, I tidy that up. So I'm going to bring a 16 out. So it's 8 times the square root of 16 into, 1/16 into 1 times 16 minus x squared on 16 times 16. And then the square root of 1/16 is just a quarter. And then I've got 8 times a quarter, so it's 2. 1/2 times the square root of 16 minus x squared. And that's in the form that it wants. Okay, a is 2, b is 16. And again, you don't have to state that a is 2 and b is 16, because it's in the form of that, so we're good. And that's the correct answer. Okay, so that was paper 2. Make sure you check that video carefully against your answers, and make sure you check out the other videos for this exam series as well. Thanks for watching.